Hello, my name is Rodrigo Cadiz. I'm one of the authors of our paper called Auditory Graphs from Denoising Real Images using fully symmetric convolutional neural networks. The motivation for work is that, as this community widely knows, people with visual impairments or blindness have really serious problems when they try to access and understand numerical information containing graphs. And graphs probably is the most exclusive and widely used way to communicate numerical data and describe numerical data, especially in scientific or mathematical fields. So our proposal is to think or use a denoising approach based on deep learning. So what do we mean by denoising? We mean that we want to treat certain information contained in the charts as noise. So we want to get rid of that information, and we want to focus only uh, on the data contained in bar and line charts. And in terms of the specific architecture we want to use, we propose to use what's called a fully symmetric convolutional neural network, which is an architecture that was previously proposed and proven to be useful for denoising problems. So what's our proposal is to take a source line chart. And of course, we have a target line chart. So we want to get rid of everything that is not the data itself. So we want to get rid of legends, access, tick marks, boxes, bounding boxes, titles, etc., text. So we want to get rid of that and get only the data. And this is how it will look in both a source, a line chart, or a bar chart. Of course, we have some constraints that we impose on our solution. So for now, we're focusing only on data extraction. So this means that our input images are already classified as a bar chart or a line chart. We don't do classification here. One of the reasons is that this is a very well-researched problem, and there are a lot of approaches that work for classifying bar charts, line charts. So we're focusing on data extraction. Um, we are focusing also in simple single lines or simple bar charts with no stack bars or anything like that. We don't take into consideration contextual information like titles, legends, access, etc. We are only interested in relative values, not the absolute value. So we're not reading the Y scale, for instance, to get the actual value. We want to estimate the relative values of all bars or the line contained in a chart. We use grayscale information, so we don't use color at the moment as any source of reliable information. And we are implementing a discrete sonification just to test how, especially for the case of bar charts. And we use the same approach because we wanted to use a unified, simple approach for sonification of both bar and line charts. So our method could be summarized in this image, in this flowchart, where we take an image, which is, as I said, is already a bar or a line chart. Then we convert it to, we scale it, we convert it to grayscale. Then we apply the neural network, and the neural network will produce, after trained, the noise image. So it's an image that contains mostly the data without the rest of the information that I told you before. Then we applied some threshold polarization and morphological filtering to get an image like you see on the right, where you have only the vars in this case. And then we apply the sonification so we can direct the sonified from the pixel information, that chart in particular. This is the architecture we use, all the layers that we use. And as you see, the layers don't change in size, they remain the same size. That's why it's a fully symmetrical network. and the input is a 256 by 256 image, and as well as the output. So this is more or less how it works. So you get the original image, and what you see on the top right is the blur image that the neural network produces. Then we binarize it, and then we post-process it to get the bounding boxes, for instance, in the case of a bar chart like that. So we compared our method with manually segmented images that we did by hand, and we calculated the mean square error in terms of its average and standard deviation. And we can see that for synthetic images, that is to say, images that we created ourselves in Python, MATLAB, or something similar, it's pretty low. So that means that when we compare what our method produces with what we segmented by hand, they're very similar. And we also tried on internet images we just downloaded from the internet. And in this case, the error is a little higher. So we think that our method works well for synthetic images that we create in a controlled software environment. Not so well for internet, where we need probably more training, and we need probably more a larger and that data set, and with a lot of more variations probably. In terms of sonification, what we use is a very simple scheme where we take pixel intensity as the main feature to be understood to do the sonification. And we associate the y coordinate with pitch and the x coordinate with time, which is pretty much the most basic approach you can use for a auditor graph. And one of the reasons we did this is that we wanted to treat the same way bars and line charts. And now I will show you some examples of how this works. In terms of future work, there's a lot of things we need to do. We need to add contextual information, that is to say, take into account title, y-axis, marks, legends, etc. Estimate absolute values and not only relative ones. If we are able to identify values on the y-scale, for instance. Add more complex sonification schemes. Probably it's a good idea to incorporate color as a source of information for the charts. Of course, we need to implement a continuous unification mode for the case of lines. We will probably need to add a classification stage previous to denoising, so we can first start with any image, tell if it's a chart, and then apply our method. We need a larger data set and more training. And of course, we need to conduct user tests to really understand the potential and application of this solution. So our approach, we think, could result in a very useful tool for automatic auditory graph generation directly from the pixel information of bar and line chart images, because they are denoised. So a denoising approach, we think, is a viable path for this task. Our code, examples, and everything related to this talk you can find it on that website. We need to acknowledge our funding agencies that made possible this research. And I thank you for watching.
So
Yeah.
I'm curious if we don't really have time for many questions, unfortunately, because we lost a little bit of time. But I was wondering if you want to tell us a little bit more about, what do you think this approach would be beneficial for in terms of
Sure.
sonifying from pixel data rather than from the actual
Yeah,
data.
well,
Yeah.
the long-term goal of this research is I would like to be able to get any image from the internet and just sonify it on the fly based on what it contains. And it's a very hard problem. So what we're first doing is trying to get the data out. That's why we're not taking into account legends or titles or contextual information, because we want to just take the data itself. So I think this works as a first step. So in the future, we would like to have, let's say, a plugin on every browser that you could get an image, and the plugin will tell you if it's a chart, and if it's a chart, it will sonify it for you. So directly from the
Wow.
pixel information. That's what we're trying to achieve in the long term.
Wow. Yeah, that's amazing. I also imagine this being really cool for images, for other images as well, outside of, charts and graphs, but you'd probably want to do more tests and evaluation, and you'd probably need to build in a bit more contextual parameters into the model.
Yes.
But yeah, very promising
Agree.
work. Yeah, thank you so much.
Thank you. No, thank you.